Okay, welcome back everyone. In this video, I want to pick up where we left off in the previous one and continue our discussion of bootstrap distributions using the golden jackal jaw length data that we were working with in earlier videos. And in the previous video, we wrote a for loop that generated a bootstrap distribution that we plotted in this histogram over here. And so to construct that bootstrap distribution, we used the for loop. And inside that for loop, there were really two actions: pick a bootstrap resample, calculate the mean of that bootstrap resample, store it, and then repeat. And this was the result. And so the whole goal of a bootstrap distribution is we would like to estimate an unknown population parameter. We've collected one sample. From that one sample, we were able to generate this bootstrap distribution. And from this bootstrap distribution, we now get a sense about how much variability there is in the sample mean from sample to sample. In this case, bootstrap resample to bootstrap resample. And so looking at how large the variability is, that gives us a sense of how much uncertainty we want to build into our estimate for the population mean. So let's see how that would work. So we have stored all of these sample means that I'm looking at in this plot to a vector which is called boot_dist. So when we ran this for loop, we stored the means from each bootstrap resample to this vector called boot_dist, and we have 100,000 of them. So that's a really large vector. And so when you have an actual sampling distribution, the way you use a sampling distribution to construct, let's say, like a confidence interval, is we calculate the mean of the sampling distribution. That's going to give us a good estimate for the population mean. So in question 4, it's first asking me to calculate the mean of my bootstrap distribution. So to do that, I'm just going to go mean boot dist, right? Since that's where we stored all of these values. And this tells me that my mean is like a little bit less than 111. So our original sample had a mean that was exactly 111. And that was this red line that I drew through the middle of the bootstrap distribution. And now we can see that those two line up very closely. So the mean of my original sample and the mean of the bootstrap distribution are essentially the same. And this is consistent with the result of like when you have an actual sampling distribution for a mean, the center of that sampling distribution typically is equal to the population mean. So here what we're saying is the mean of the bootstrap distribution is essentially going to equal, or at least be close to, the mean of our original sample. But we do not know if the mean of our original sample is close to the population mean, right? We don't know what the population mean is. So in order to get a more kind of robust estimate for this population mean, rather than just say it's 110.99895, we like to build in a margin of error and say plus or minus. And the how large the margin of error that we're going to build into this estimate depends on the variability in the sample statistics that we can see in our bootstrap distribution. So we're going to measure the variability of this bootstrap distribution with the standard deviation. So when we calculate the standard deviation of a sampling distribution, we call it the standard error because in some sense it is related to how much error we want to build into our margin of error. So we're going to calculate the standard deviation of our bootstrap distribution. And we can see that is about 0.84. So this is measuring the variability in the sample means that we get. And if you remember from construction of, say, like a 95% confidence interval, what you would typically do is you would take the center of the sampling distribution and go plus or minus 2 times the standard error. And that's going to have a 95% chance of containing the actual population mean. So one way that I can construct an interval estimate would be to take the center of the bootstrap distribution and then go plus or minus 2 times the standard error. So rather than say, I think the mean length is 111, we say that the mean length is 111 plus or minus 2 times 0.84, for example. And now we've incorporated some margin of error into our original estimate. But one thing that comes up with bootstrapping is we don't always get a symmetric bootstrap distribution. So you can see over here, I have a little bit of a tail in this distribution to the right. So this is not exactly a normal distribution. So we don't really know whether we want to go 2 times the standard error to the left and to the right. And these distributions might not even be symmetric. So in the next video, we'll talk about a different way that we can construct a confidence interval estimate from a bootstrap distribution.